If you're anything like me, your intuitive notions about magnetism are partly right and partly wrong, despite your experience with permanent magnets, soft iron, Canadian nickels, compasses. Probably never occurred to you that in the free atomic state, roughly half of the atoms in the periodic table are as magnetic as iron. These atoms are small permanent magnets, as strong magnetically, weight considered, as a piece of alnico. Using this apparatus, we'll demonstrate the magnetism of individual atoms by deflecting them with magnetic forces. But more than that, you'll see, perhaps you already know, that magnetic atoms can't just have any orientation in a magnetic field, an effect that can only be explained by quantum theory. An experiment similar to the one you'll see here was first done in 1922 by Professor Otto Stern and Walter Gerlach. Their experiment was with atoms of silver. We'll use atoms of cesium instead, even though cesium metal in its condensed state, and here's an ampule of it, is just as lifeless magnetically as most things. But before we get on to atomic cesium, let's get straight the basic question of the magnetic forces involved. What do magnetic dipoles do in magnetic fields? A compass is just a magnetic dipole that points north. So, to be sure, it always ends up that way, but if it isn't that way initially, it oscillates about the field direction for a while before friction brings it to rest. If atoms behave just like compass needles, then isolated atoms in vacuum, free of all friction, would oscillate about the field direction forever. In our experiment, we're not concerned with the oscillations, but with the net force on a magnetic dipole. Now, there are two orientations of special interest that we'll look at. We call them parallel or anti-parallel to the field. Here's a pair of Helmholtz coils with some iron filings. With current in both coils, we get a uniform field, smack in the center. When we put a magnet in the center, it oscillates about the field, but there's no net deflection in any direction. See? Now let's switch it off, on, off, on, off, on, so. Now we carefully set the magnet anti-parallel to the field in the direction unstable against rotation. This is the unnatural position. Our intuitions are sort of against it. To be sure, if it gets off its unstable equilibrium the least bit, it'll swing around, so I have to get it just right. It still doesn't tend to translate in the field. Off, on, off. In a uniform field, there's no net force on the magnet. Now let's see what happens in a non-uniform field. We'll put current in only one coil. You can see here the field is non-uniform. It's strongest where the field lines are crowded together. We put the magnet back in the stable position, and it tends to move toward the coil with the current in it. Off, on, it moves into strong magnetic field. Off, on, off. Now put the magnet back into the unstable position. It's a non-uniform field, of course. Anti-parallel. It's not so easy. Just there. On. There it goes. It moves into weak field, see? Off. On. Off. In a non-uniform field, then, there is a net force on the magnet, which depends upon the way it is oriented. Now, how big is this force? You know how to calculate it, thinking of the small magnet as having equal but opposite poles at its ends. Then the net force is just the pole strength times the difference of field at the ends. But if the magnet lies along the field direction, parallel or anti-parallel, the difference of field is just the field gradient times the length of the magnet. Calling the field direction Z, we can say that the force, F, is equal to the dipole moment mu times the magnetic field gradient, dB by dZ. To get a strong non-uniform field, we can use an electromagnet with special soft iron pole pieces with a cross-section like these. This powder pattern shows the kind of field you should get. Here is the iron, and here is the space between. It's strongest, the field is strongest, near the convex pole piece. If a small bar magnet is placed in the parallel orientation, it feels a strong net force pulling it toward the region of stronger field. It tends to fall into strong field. Whereas in the anti-parallel case, there's a repulsion on the side where the force is larger. So it tends to move into weak field. And so if atoms with magnetic dipole moments enter a non-uniform field like this, they'll be pushed one way or the other according to their orientation. Now, in the experiment itself, we can't just place atoms between the poles of a magnet and measure the forces on them. Instead, we send a stream of atoms between the poles in a direction perpendicular to the field, like this, and observe their transverse deflections. Here's a schematic of the apparatus. Atoms emerge through a narrow slit in a small container, which we call an oven. A fraction of them get through a narrow collimating slit. As they pass through the magnet, their directions of motion are slightly changed by the magnetic forces. And at the other end of the apparatus, there's a small detector which can be moved transversely to explore the deflections caused by the magnet. We also have a shutter in front of the oven that can block the whole beam before it enters the magnet. And between the magnet and the detector, we have an adjustable shutter. Of course, the apparatus must be in a good vacuum so that atoms can travel from source to detector with negligible risk of collision. Now let's look at the parts of the apparatus. These two round metal containers make up the oven. We put a cesium ampule into the back one. We break it there after it's in a vacuum because cesium is so active chemically, much more active than its near brother sodium, with which you're more familiar. We warm the oven, you can see the heating coils, to vaporize the cesium, which fills both containers. Some of the cesium atoms escape through this 10th millimeter slit. Directly in front of the oven slit is this shutter, which can be moved from the outside of the apparatus by hand with a small bar magnet. And now from there, the beam goes through the collimating slit, the jaws of which are made of stainless steel razor blades. The two other blades fix the height of the beam. The width of this collimating slit can be set from the outside with a control. The transverse position can also be set from a control so that we can aim the ribbon-like beam of atoms directly down the magnet gap. Here's the magnet. The shaped pole pieces are made of wafers of soft iron stacked and bolted together. The pole pieces are quite long compared to the gap. The pole pieces slip into a piece of glass tubing that carries the vacuum, and the whole thing fits into the magnet so we can have the return yoke and the magnetizing coils outside the vacuum system. These rather large coarse jaws can intercept the beam after it leaves the magnet, but we'll come back to them later. The detector is a 10th millimeter niobium wire. When hot, this wire converts any neutral cesium atoms that strike it into positive cesium ions. The ions are collected by this small negatively charged plate. The current in the plate circuit, which is our measure of beam intensity, is amplified and recorded on the y-axis of this XY plotter. The x-coordinate indicates the transverse position of the detector, which is moved by pushing on it. The push rod can be moved from outside through these bellows worked by a knob. The whole detector assembly is covered with a wire screening to ensure that the sensitive circuit really measures the beam and doesn't act as a burglar alarm. Here's the apparatus ready to run. Now, we really made the second half of this film before the first. This means that we don't have to wait around for the vacuum pumps to work, to find and fix all the leaks in the vacuum system, to work out other bugs that always beset every experiment. So here goes. The oven is already warm. The magnet power is off. The detector wire is hot. Now we open the shutter and move the detector across the beam. The pan deflects. Then it levels off. The detector current at the peak is about 10 to the minus 11 amperes and corresponds to about 10 to the 8th atoms per second hitting the detector wire. There's the beam. One large division on the x-axis is equivalent to a detector movement of 1.3 millimeters, so the beam's about 2.7 millimeters wide. If we go back to the center of the beam, we can insert the shutter and cut the beam off. On, off, on. Now, just to show that we know what we're doing, we'll narrow the collimating slit. This, of course, should make the beam narrower. There it is. Now we'll begin the main measurements, leaving the beam narrow. First, a clean trace of the beam with a magnet current still off. We've turned down the gain of the detector a little bit, but that doesn't matter. Next, we move the detector back to the middle of the beam and get ready to turn some current on in the magnet. The field intensity with one cell of this battery will be about 2,500 Gauss, and the gradient, which you remember is the important quantity, is about 3,300 Gauss per centimeter. The beam intensity in the middle falls. It's a little less than half its former value. Those atoms must have gone somewhere, so let's explore the beam again. The beam has been broadened, symmetrically you notice, showing that cesium atoms are in fact magnetic and are deflected in either direction by the magnetic forces. But let's see what happens when we increase the magnet current some more. Two cells give us about 5,000 Gauss and a gradient of about 6,600 Gauss per centimeter. The pen begins to deflect sooner. But then right in the middle, where most of the atoms were before, there are now very few, and the rest come over here. The atoms have been deflected equally to both sides. As they pass through the magnet, half of them were forced in the direction of stronger magnetic field, and the other half were forced toward weaker field. Let's increase again to about 10,000 Gauss per centimeter. The two wings are separated and broadened still further. And now there's almost no intensity in the center. We can show that by closing the beam shutter and making the trace again. Now, how can we go about accounting for these particular magnetic deflections? We know that the atoms emerging from the oven have a random thermal distribution of speeds and are also randomly oriented. What would such atoms do if they were really little bar magnets, like this one sitting in a frictionless air bearing? Each atom, while in the field, would oscillate very rapidly about the field direction. The range of angles depends on its original orientation. An atom like this, passing through our apparatus, would at the same time be pulled sideways by the field gradient. Its final deflection would be the result of a kind of average over its oscillations. This curve shows the kind of beam shape to be expected in that case. One would find atoms deflected either way, but the curve is asymmetric. The compass needles are more likely to move toward the stronger field. But we saw that that doesn't happen. Even when our magnetic field was too weak to reveal the splitting, we saw that the deflection pattern of the beam was symmetrical. Now suppose that the atoms are little magnetic gyros like this one when we spin it. Comes nearer to the truth, for we know that there's an intimate connection between angular momentum and magnetic dipole moments of atoms. This magnetic gyro has a stability. The angle between its spin axis and the magnetic field remains constant, even though the gyro precesses about the field direction. Thus, even an atom starting out at a large angle to the field would remain with that large angle to the field. If our atoms were like magnetic gyros, randomly oriented, the beam would be sped symmetrically, as in this curve. But clearly this won't fit our data, because there'd always be a hump in the middle, however large the field gradient. And so to explain these data, we have to use a quantum model. The atoms are quantum gyros restricted to a few discrete orientations in a magnetic field. With our cesium atoms, we see evidence for only two orientations, parallel or antiparallel. The thermal distribution of speeds, of course, smears everything. Slow atoms spend longer in the field than fast ones and undergo bigger deflections, so we get lumps rather than sharp bumps. Here's a curve calculated according to quantum theory, and it looks very much like our data. The agreement is still closer if allowance is made for the finite width of slit and detector, thus smearing the theoretical curve even further. When the Stern-Gerlach experiment was first performed in 1922 with a beam of silver atoms, no one knew what to expect, or rather, people did think they knew, but they didn't quite agree. Some thought the beam would not be affected at all, some thought it would simply be broadened, and some, including Niels Bohr himself, thought it would be actually split. And even some of those who expected a quantum splitting were surprised at the hole in the middle, the complete absence of an undeflected component in the beam. This was a decisive experiment in the development of quantum theory. Now, before we end this film, let's do one more simple experiment. You'll remember that we have some movable jaws between the magnet and the detector. We'll insert one of these jaws so that it cuts half the split beam off. This means that we could work, if we wanted to, with this beam of atoms, all oriented in one direction with respect to the magnetic field. The placing of the jaws was not quite perfect in some sense. We could make it better, but most of the other beam is missing. Now we pull out the first jaw and put in the other. And we get a beam of atoms all in the opposite orientation. This opens up the possibility of doing experiments on selected magnetic quantum states of atoms in an atomic beam. It's a work which I happen to like. I began this film by saying that cesium atomic dipoles are as magnetic as iron. Here are data from this experiment that you can use to show that this is so. The magnet length is 12.5 centimeters. The distance from the end of the magnet to the detector is 50 centimeters. The oven temperature is about 400 degrees Kelvin. And the distance between the two peaks is 3.7 millimeters. when the field gradient is about 10,000 Gauss per centimeter.